Hello, my name is Joseph Ayali. I'm a member of the Coherence development team. I'm here to talk about a new feature added to Coherence 14.1.1, a messaging capabilities provided by Topic API. Specifically, we'll be talking about subscriber group functionality. This video illustrates by a source code example on how to increase message throughput by parallel consumption of subscriber group values. By the end of this video, one will have learned how to configure a topic publisher and subscriber to meet the requirements of the example. This source code example is part of the topics examples and coherence examples that's part of Coherence 14.1.1 release. We're going to concentrate first on the example. So there's a job value that's published to the topics, and the job object has two different states. It has a creation state, and it has a update state. So when the job is initially created, it's a create state, and then it's either updated to either be completed or canceled with an end time. It is important for this demo that the order of the messages is preserved, and when a publisher publishes the messages, the create is published and then the update is. And we're going to look over various options on how to preserve that ordering in the topics publisher. So when the topic publisher is created, by default, there's 4 different order by options for preserving the order of the messages being published, the order they're sent. So by default, the message ordering is per thread. So if a publisher is running on a thread, all of the messages sent from that thread will be stored sequentially in the Coherence data grid. We will go into more detail on these options as we go through the example, so I'm not going to go through them. Just the whole purpose of the demo is to show where to use these. So job subscriber group example. So first off, we have the Coherence storage data tier that has a configuration file, and inside that configuration file is configured a job topic. So we're going to go look at that source code. So this is a Coherence configuration file, and it has cache mappings and topic mappings. Right now we're concentrating on the topic mapping. There's a job topic, and it has this is the fully qualified Java name of the values that will be placed in the topic. And additionally, it defines a subscriber group, job queue. So when this topic is created, this subscriber group is immediately created also. So we're guaranteed, when you define it in the configuration file, you're guaranteed that this job queue will never miss a message sent to the job topic. This doesn't need to be declared ahead of time. This is a durable subscriber group. If one just creates a subscriber group on the fly, it works also. It just this has an added guarantee of values not being lost. Here's what the job class looks like. It implements a Coherence portable object. It's beyond the scope of this talk. It's a serialization mechanism, and it could just as easily be Java serialization. And here are the 3 different states that a job can be in. It can be in a creation state, a canceled state, or a completed state. So we have showed how to declare the job topic in a configuration file in the job queue. Now let's go look back at the source code to show how to access it in a Java program. So within the Java program, the entry point to getting to the Coherence is through session.create. and that's in a try with resource block because it's auto-closable. Additionally, the topic that we're working with, the job topic, from the session we say get topic, the name job topic, and then this value type assertion with type, as I had showed in the configuration file, it was specified the fully qualified name of the job class. And so now we're using generics with the topic by doing this value type assertion. I'd like to also show that there's many different flavors of this. So we can do with the specifying the type. We can specify without type checking. And you can say just use with raw types, and then you could just use name topic and not use generics at all. By default, it's without type checking. So now we've shown how to get access to configure the job topic in the subscriber group and get access to it. Now let's show how to configure a topic subscriber to be a subscriber group member. We have two subscriber group members subscribing to a job queue. So here in job subscriber group consumer, we passed in a topic when we created it, and we're using that topic to create a subscriber, and we're passing in a subscriber group option. So let's look at the Java doc for options. So for a subscriber option, these are all the different options that when one's creating a subscriber, you can specify. The one that we care about at this point in time is a subscriber name of string. So this one specifies a subscriber group name. If you create the subscriber without any options, it's what we would call an anonymous subscriber, and it would be participating in a publish subscribe model where every anonymous subscriber receives messages delivered to the topic. But if you specify that the subscriber is a subscriber group member, then it enables for each value that's in the subscriber group, one and only one subscriber group member processes it, and it allows parallel consumption of messages. So after we create the subscriber, and it's in a try with resource block, so it'll auto close at the end. And point out you can do subscriber. You can have a Lambda method that allows you to specify an action to be executed when the subscriber is closed, so you could be notified asynchronously. So we have a while loop that will continue working, calling subscriber.receive, asynchronous. So here's the receive. So the subscriber.receive receives a value from the topic, in this case the subscriber group on the topic. If there is no values available, then a future will complete according to subscriber complete on empty. So if you do a lot of subscriber receives asynchronously, they'll all be waiting, and we process things more in a block manner, and it's much more efficient network-wise. So now we're going to go back to, now we have the two subscribers waiting to receive messages. And now we create a publishers. For our example, it automatically creates 4 publishers and 4 subscribers at the same time. For the slideware, it's just more convenient just to show 2. So the first example that we're going to show running is the default of Publisher.OrderBy.thread. So the job publisher is going to be sending these messages. So now at this point, let's go back to the source code and see the creation of the publisher with this option specified and how it goes about sending these messages. But these messages, I'm showing them in blocks because we under the covers we block things together. But this is a job 11 create, a job 12 create, a job 11 update, a job 12 update. So they're not consecutive, but they're in order that a creation occurs, and then later on the thread does an update. So that's the ordering constraint that we talked about for the example that needs to be preserved. Okay, so here is the job publisher. And the job publisher, we'll look at the options that you can configure. So here's the Java doc for the options for a publisher. And the ones that we're concerned with is Publisher.OrderBy. So there's 4 different kinds of order by. Order.by.thread, which is the default, and that's the one we're working on. So each thread, the messages sent by this will be preserved when they're stored in the data grid. So we create the publisher with that option. And it's in a try with resource block, so it'll be auto-closed at the end. Note, I'll point this out now, since there's a loop that's publishing many job objects, when that loop's exited, we have outstanding asynchronous messages. And since we're going to be performing the close, it's a good to call publisher.flush.join to ensure that you wait for all outstanding asynchronous sends to complete before exiting a try with resource block. But for this the publisher is given, when it's created, it's given a how many jobs it should publish and a little bit of a prefix for the jobs and whatnot, and what order what the ordering constraint is for the publisher for preserving the order. So for this example, we generate a job, and then we publish that job. So this method is publishing the job to the topic. We'll go look at it down below after. And then after we publish the current job that we generated, we look at the previous job in the loop, and we send an update of the job status. So we update it to either be completed or canceled. It's just randomly, and we just iterate. So you're always guaranteed that the create occurs before the update on the status from the publisher's point of view. Let's go look at the published job. So the published job sends job to the topic either synchronously or asynchronously. So our method on publisher, the send method, the Java doc for the publisher.send states that we asynchronously publish the specified value to the topic. So what that means is we do the send and return immediately with the future. If we do a join on the future, then we turn the asynchronous send into a synchronous and ensure that there's not another send before this one completes. So that's the synchronous send mode. The default mode for this application is asynchronous, so it has an asynchronous on the future to say when it's completed, increment the number of sends that we're counting, decrement the number of outstanding sends, and then if verbose mode's on, it actually prints out all the information. When you run the Coherence example topic, by default it will print out the verbose mode. For running the demo, we'll be using terse mode. So if it's in terse mode, then we'll just be printing a dot every time a message is sent. And this also, if If an exceptional condition occurs, you can print out the exception. Exceptional conditions could be someone deleting the topic from underneath you, or you specified a maximum size for the topic, and this could be ran out of storage space. So those are possible exception states. So now the job publisher has sent it. It's doing a send for these, and those get written because the publisher was created with order by thread. When it's written into the data grid, it's written into abstraction that preserves the representation between the order that they were sent in. Additionally, we're going to show the other publisher sending all its messages. So for this example, we can see all the job 1s were from the first publisher and all the job 2s were from the second publisher. Now we're going to be consuming the messages. So let's go back and look at the subscriber consumer and see what we do in the handling. So when we receive a message asynchronously, here are the steps that take place. Well, the first step is checking for a terminating value, indicating the publishers have finished. So when the publishers have completely finished everything, they send this constant terminating job. And this is the way the subscriber gets notified that its process is complete. It sets itself to not active anymore. So we'll exit the loop. So if we've received a regular job, the very first thing there's logic to validate that the job values that was sent by the publisher, the order has been preserved when consuming the value. So the first thing it does is this job one that was a creation job, or is this an update job based on it being completed or canceled? So if it is a creation job, we're using a coherence cache to put if absent. So we're checking a cache that can work across JVMs. It's also on the data grid. And we're putting a cache based on the job ID and the job. We're checking to see if it already exists. If it already exists, then we probably got it from the completion coming in first. And then we log that there was a creation failure, that we received messages out of order, and we print an X when we're in terse mode. We print the warning when we're in verbose mode. Additionally, if the job is completed or canceled, there's a validation check, and it tries to, using the coherence cache map, it tries to do a replace, making sure that the job is exactly what we expect it to be, a creation job, and that now it's a cancel or a complete. If the replace returns false, then we've detected that out of order processing has happened, and we print an X. So now we're just going to complete. Whoops, too fast. So now we're going to show the messages were consumed by the subscriber in the order that they had been put in by the publisher thread. Now, having the publisher specify the ordering is required to be able to consume an order, but we are missing a subscriber option to make them sticky to the abstraction of within the data tier. So while these examples, the ordering is preserved, if we're across different JVMs and stuff, we might see out of order. Okay, so now we're going to do this example is actually going to be the example that shows the ordering that's the best for this example. So we're going to be creating a publisher with order by value using job hashCode. Let's go look at the source code. That's an awful lot to digest. So when one specifies on the command line minus order equals thread, this is where we would come to. It turns into a Publisher.OrderBy.thread. So for Publisher.OrderBy.value, we come to this step. And so when we specify value for this example, the specific constraint that we originally discussed was that for a job, we only needed to preserve the ordering between a job and its update. And by doing the job by its hashCode, so let's go look at its hashCode. So order by value takes a unit of order based on the sent value. So based on the value that we're sending to the topic, you can call any operation on it. For this example, the hashCode intentionally does not include anything to do with the state of the job. All it is the job identity, and it enables the ordering for a job that for the same identity to be all ordered together. And so that's why this unit of order for this example works. And just to remind, so when we created the publisher, so that value is going to be passed in with the reference to the job hashCode as being the unit of order for the jobs. Let's go back and see how, by using order by value, how that influences the messaging. So we're showing that the only constraint that needs to be preserved within the storage tier in the subscriber group is that the jobs that have the same hashCode, so job 11 create, job 11 update, which is either canceled or complete, those are of all the messages that are here, those are the only two that needed to maintain the order. So this lessens the constraint that by thread had and allows more efficient under the covers processing to increase parallel consumption. So now the job 12 and the job 12 are written in another abstraction that maintains ordering. And additionally, for this publisher, the only constraints that needed to be was that job 21C and a job 21 update. So these are in abstractions that within the data grid, the only requirement is that the subscriber group members process these, not that they process them in the order that they were by thread. So now you can see that before the job, all the messages sent by the job publisher when we were using thread were all sent to one subscriber. Now different subscribers can process them because the constraint for the messaging wasn't the same. So now that we've gone through that in slideware, let's actually look at the demo. So we're going to start the subscriber groups. And now we're going to, instead of doing order by thread, we're going to do order by value, which ends up being the best. So as we're confirming that the 4 subscriber groups are ready to process. And the subscribers are all receiving each dot they're receiving. And as we can see, each subscriber processed and didn't find anything out of order and processed 2,000 messages. So now the last example is going to be the order by that maximizes parallelism because it doesn't preserve any ordering between any of the messages sent by the publisher. So if the values don't have any ordering, then this is by far the best to use. But for our example, it's not appropriate because we would like to preserve the ordering between create and the update. So to show in the slideware how this works, is we have all the messages, and they all go immediately. There's no ordering constraints, and they're immediately all processed by the subscribers, but there's no ordering constraints. The order that they're received in has nothing to do with the original job publisher. And so now if we go look at the example, we're going to specify none. And you notice I didn't really start the subscribers before the sender this time. It doesn't make a difference what order, since the subscriber group is defined on the job queue is defined on the topic. It didn't matter if any of the subscriber group members existed. The scope for job queue was already there. As you can notice, many X's came up, many. So we counted 456 invalid jobs in the cache, all out of order. So that shows, while that is the fastest and the preferred way of doing it if there's no ordering, order by thread was selected by default because it's most likely people would like that preserved. But to optimize a value throughput processing and consuming, this is the best option if there's no semantic constraints between the messages. So now that we've gone through this, the default is thread. All the values sent from the same thread are stored sequentially. We showed that for this example. We didn't look at order by ID, but it is worse than thread in that for this example, if you specify order equals ID on the command line, it will specify, the way this example is written is all the threads will write to ID 1, and in that case, it's worse serialization than doing it by thread. We're actually saying that it matters what time they were sent at. So very quickly, we'll go through this messaging throughput consuming from a subscriber group. So if one has all the publishers using the same order by ID, then that means that all of the messages in the Coherence data grid have been serialized. And independent, on the bottom axis, we have 1 publisher, 1 subscriber, 3 publishers, 3 subscribers, 6 publishers, 6 subscribers, and this is the message, the processing rate that we can run at. Notice when all the publishers are using the same thread, and all the messages are serialized, that no matter how many subscribers we throw at it, we can't improve throughput because to preserve the constraint of ordering, everything gets slowed down. Now, when we're using order by thread or order by value, and there's a unique, the channels are an abstraction underneath that enable to keep the sent messages sequentially. Then we are able to, for thread and for ID, we're able to scale up. When we have 1 subscriber and 1 publisher, we're at this rate. But if we add 3, we're able to double our throughput. And if we add 6, we're again able to increase our throughput. So we're getting linear scaling based on the number of publishers and subscribers when we use order by relaxed constraints, ordering constraints, and not ordering everything by the time they were sent at. So that concludes our demo. Just a reminder, the source code used in this demonstration is available in Coherence examples in Coherence 14.1.1. Additionally, there's a topics intro that's a lot more detailed on using the API. This video was just to concentrate on subscriber groups and configuring Publisher order by. Thank you.